rational root theorem. It is also known as the rational zero theorem. So roots and zeros all mean kind of, they have the same meaning, and I'll use those terms interchangeably. Now, the definition for it is a little bit confusing. If you're not well versed in the witchcraft of mathematics, that's sometimes what it looks like. It's witchcraft. So here's the actual theorem stated. If p at x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 on down the line to a sub 0, and a sub n cannot be 0, then we wouldn't have the polynomial term. And p divided by q is a rational zero in lowest terms of p, then p is a factor of the constant term a sub naught, and q is a factor of the leading coefficient a sub n. So what does that mean? That looks all fairly confusing. So let's say we had a function. Okay, a sub n is this 4. And a sub naught, or the initial a as it's sometimes referred to, is equal to 12. Okay. P, right here it says P is a factor of the A0 and Q is a factor of the AN. So we just need to find out all the factors of A0. So all the factors of A0, so we'll call those P. So P could be 12, 6, 4, 3, 2, or 1. Those are all the factors. And they also could be positive or negative. We'll talk about that in a second. Q is all the factors of a sub n. Well, all those factors would be 4, 2, and 1. So those are all the factors of 4. So what we need to do, and what this does is it narrows the search for roots or for x-intercepts in this function. That's what the rational root theorem does. And so we're going to narrow it down to just a few, a handful basically, so that when we have to go in and divide these functions out to find the rest of the roots, we narrow our search to kind of save some time. It doesn't seem like we're saving much time, but there it is. So now we're going to look at p divided by q. Our rational root is of that form, and it can be of any combination of the p's and the q's. So you got to go through all the combinations, and I'm going to go through them all, but typically when you do this, you kind of go through them in your head and say, oh yeah, that reduces, but I'll show you all of them. So we'll start with the 12. So you could have plus or minus 12 divided by 4, plus or minus 12 divided by 2, plus or minus 12 divided by 1. And that way I don't miss any. But you notice those reduce. So they all reduce it down to so that would reduce to really plus or minus 3, plus or minus 6, and plus or minus 12. Okay, so those are all possibilities with the 12. Other possibilities of P versus Q. Now let's move on to the 6. So you could have plus or minus 6 divided by 4, plus or minus 4, sorry, I went to the wrong one. Plus or minus 6 divided by 2, I'm trying to jump ahead. Plus or minus 6 divided by 1. So those are all the PQs for 6. And again, they reduce. So you could have plus or minus 3 halves, plus or minus 3, which, that one's already, we already know that's a possibility, and plus or minus 6, which we already know those match up. So we've only found two new possibilities, plus or minus 3.5. And you just keep going for all of them. So now we'll move on to the 4. So plus or minus 4 over 4, which is 1, plus or minus 4 over 2, which is 2, and plus or minus 4 over 1, which is 4. So we added some new ones here. We've got plus or minus 1, plus or minus 2, and plus or minus 4. So I guess we have 6 more of those. Yeah. And so those are all new possibilities. Okay, and you just keep going down the line. So now we're going to go 3. So now your rational root could be plus or minus 3 over 4, plus or minus 3 over 2, which we already have, and plus or minus 3 over 1, which we already have. So the only new one that we got out of that is plus or minus 3/4, and so that's the only one I'll write down. So those are roots for that one, or possible roots for that. Then we go to 2, and if you look at it now, hopefully you've got the picture. We'll just kind of do this in our heads here. 2 over 4, like here and here, is 1/2. And I do believe, oh, we don't have that one. Amazing. We are going to pick up another one. So plus or minus 2 over 4, plus or minus, we'll just go through them. Plus or minus 2 over 2, plus or minus 2 over 1. And again, we already have this one. We already have this one because that's 1. This is the new one, plus or minus 1/2. And then the final one is 1. So we'll go through the 1 divided by 4. So we've got plus or minus 1 divided by 4 as a possibility. We've already got 1/2, and we've already got 1. So we've added this to our possibilities. So our list, so we need to go through that and just list out the ones that aren't repeated. And all of those are potential roots for this equation. So if you think about infinity, and we have an infinite amount of numbers to choose from as rational roots, at least we've narrowed down the search to something manageable, something we can do. To narrow it even further, all the x-intercepts are going to be rational roots. So, so here I've graphed the equation in GeoGebra, and I'm going to go ahead and intersect the function and the x-intercept. And so 3.65, negative 3.65 is one of my roots, and it'll be on that list. We'll find it here. Negative 0.25, 1.65, and 20. And you know, I'm looking at negative 3.65 and 1.65, and I'm wondering if I don't know that that is part of my list. So let's go look back at my list. Now, negative 0.25, that's negative 1/4. I know that one's there. And 20, 2 is also there. So those are 2 roots that are potential. It's possible that 3.65 is irrational, a pair of irrational roots that we have in this. So you look at our list, there's the 1/4 in green, and then plus or minus 2 right in that location. So those are located, but I'm not seeing 6/2. I'm not seeing anywhere where we would have the potential to get negative 3.65. So I'm assuming those are irrational. One way we could kind of tease out, not that this is a proof by any means, but we could go in here and round, maybe go 15 decimals and just see what happens. Yeah, just as I suspected. If you look at that, negative 3.64575, that looks like an irrational number. Granted, it's rounding at the end to end it, but it looks like we got 2 rational roots and 2 irrational roots in this function. Unfortunately, rational root theorem doesn't allow for the irrational roots, so we're going to have to do something else for that, and that'll be in the next video, is how to determine your roots, for all of your roots, starting with your rational roots. So I hope this helps you understand rational root theorem. We've got a big list to deal with, but we've already pared it down to two rational roots with the graph after we do it. Now you could go straight to the graph, but I think there's some value in having the list, because in the next part I'll show you how you start using the division of the synthetic division to kind of help you get all of the roots, because we want to find our imaginary as well as our irrational as well as our rational. So best of luck, and I will see you next time.